So welcome to Cal 3. How many of you were able to log into ACES and check your email? Anyone do that yet? 1, 2, 3, 4, 5. No? Diego, Josh? Yes? Okay. So when you log in, I should have sent you an email already about this course. I had a video. It was, how long was it, like 15, 20 minutes, something like 18 minutes? And it goes through the whole syllabus and all the stuff that all the expectations of the class. So I'm not going to waste time doing that. What I will mention is that in case you don't know how to get to ACES, it's here. And this looks like it's running really, really slow because that took forever to load, didn't it? This happens every semester. First day, all the technology falls apart. So, yep. All right, so I'm going to assume you can get into ACES, all right, and watch the orientation video. Come on in. Cal 3? Okay, have a seat. We might have to wait till, well, I can't wait till next time. Let me try this again. Okay, you log into ACES. Here we go. Maybe it's back. Yeah. So when you log in ACES, you go to your courses, and Cal 3 should be listed here. This is going to take you to a separate place, which is called Canvas. I talk about this all in the orientation video that I sent you, but there's something in particular I want to show you. I just added this morning. Yes. That basically means the system has failed and it's fallen apart, can't handle the load, and yeah, so can't show you. But on the main page for the class, there's a brand new link. It says click here for the syllabus confirmation quiz. And what it is a little quiz. You just answer yes or no. It says, did you read the syllabus? Have you watched the orientation video? Yes or no. That is due on Wednesday at 11 a.m. So right before class. Sometime between now and then, you need to go check yes to basically you're signing the syllabus there, and that's what you're doing. And that way, if you ever say, well, I didn't know, I can say, yes, you said you did, right? So that's our little agreement, okay? So please do that. We are in Cal 3. My name is Robert D. Giovanni. I teach full-time here. I have a very interesting semester. I haven't taught this particular setup in a while. I'm doing Cal 3, and then I'm doing Cal 1 right after this in this classroom, and then tomorrow I'm doing Cal 2. And those are the only 3 face-to-face classes I'm doing, Cal 1, 2, and 3. So I like that because I like teaching calculus, so it should be fun for me. So after this class, we end at, what, 12:40? And my next class starts at 1. And I'll be in here so I don't have to leave, or, so I can hang out for a little bit after class and talk if you need to, which is good. Also, before this class, I'm in my office at 9 a.m. So for 2 hours before this class, you can come in for help. All right? I'm pretty much ready to start, but I feel like we need to have a little bit of like, hey, let's get to know each other, but I don't know if y'all feel like doing that. If you haven't watched the video, you'll know what this is all about, this whole microphone setup thing. I'm recording all this right now. I'll post it on YouTube later on, and then you'll be able to go back and watch everything, and, you don't have to, but it'll be there, okay? I'll be presenting my lecture notes, and then also I'll be writing down using OneNote to write, go through examples and stuff, and all that's recorded, and so it should be interesting. Let's talk a little bit about the philosophy here for Cal 3. How many of you have heard that Cal 3 is easier than Cal 2? It seems to be what I hear a lot. Anyone hear Cal 3 is harder than Cal 2? No? Okay, Here's my philosophy, my experience with it, okay? I think that the concepts in Cal 3 aren't any more difficult than what you saw in Cal 2. If you were challenged in Cal 2, you know, you went through all the integration techniques. How many of you got to see a good treatment of series? Series, power series, Taylor series, convergence tests, all those things. If you saw that, then you kind of already have reached almost the peak of the challenge of calculus, I think. So what makes Cal 3 different is that you're in, at least, at a minimum, you're in three-dimensional space most of the time. So if you're in three-dimensional space and we're trying to put these things, I'm trying to write things on a board, it becomes very challenging to put 3 space onto 2 space, right? And as a student of Calculus 3, when I was a student, you know, I had the professor up in front of the huge auditorium on a chalkboard that I could barely see, and he's drawing three-dimensional space, and I'm trying to for the first time draw 3D space myself on a piece of paper, and that became really the heart of the challenge for me was trying to visualize things three-dimensionally. So for me, what I've done is I use this program, Wolfram Mathematica. You've probably heard of Wolfram before. You've heard of Wolfram Alpha, I'm sure. This is the same company that supports that website. They have a math program. It's the core of their company, basically, is this program, Mathematica. And it's all C+ based programming. And so what I've done is I've been programming in Mathematica since version 4.1, and I think they're in 8 point something. So like back in the 90s, I was programming in Mathematica, and I've been doing it since then. So everything that you see here, all these notes that I make, most of them are interactive. You know, this is a very generic one right here, but all of that's coded in Mathematica. So I will be presenting things in Mathematica, and what we'll be able to do is we'll be able to look at things three-dimensionally. This is not a good example, but can you all tell that's three-dimensional space? You know, maybe if I show you a plane in three-dimensional space, that might be a little easier to see. Okay, just imagine me trying to draw that on the board, and you trying to draw that and follow me. So what I think I've done in this class is I've really helped bridge that gap between the visualization part of it, and so that leaves really the theory is what's left for us to go after, and it's not more challenging than the Cal 2 or 1, in my opinion. However, because this is Cal 3, I will challenge you beyond what you got in Cal 2. So what I like to do in this class, since it's the end of the calculus sequence, is the problems that I give you, you're going to get a lot of take-home problems, take-home quizzes. And a lot of those problems, you will not find examples of those in the book. You're not going to be able to go online and Google it or anything like that. They're going to be problems that I made up, that I made sure that it was going to force you to possibly go back to Cal 2, go back to Cal 1, and really just kind of bring everything from calculus together into these problems. The book problems are very much, you know, here it is, do the problem, very mechanical, like I talked to a couple of you about, very mechanical. You know, here's an example, now you do one. Here's an example, now you do one. I avoid that in this class because, you know, you need to be challenged, right? This is Calculus 3. So be prepared for that. Anything else? I am changing the way I do Cal 3. Normally, what I've done in the past is I used to have 8 take-home exams. And these exams, I didn't bring them with me, but they are long and they're very difficult exams. And usually after the first 2, it weeds out all the people who don't understand what, you know, what level of work is required. The problem with those exams is, honestly, they're a lot for me to grade because those take-home exams that I was giving were on average 5 to 10 problems, and they would take you on average 12 to 20 hours each to do. You know, because they're about an hour to 2 per problem. And so grading those was just a nightmare. You know, it was just, I get those every week or 2, and I'd have to grade them. So what I've done for my own sanity and my own, just kind of notch it down for myself a little bit, is I'm going to give you take-home quizzes, and what I'm going to do is I'm going to take some of those problems from those exams. I'm just going to pick my favorite ones. You're not going to get the whole take-home exam. You're just going to get pieces. Does that make sense? So I'm kind of notching it down a little bit. Like if you would have taken this in the spring, it would have been a little bit harder. This class would have been a little bit harder. So if you do not feel appropriately challenged, if you feel like, you know, I'm not pushing you hard enough, there are people out there who want to be pushed hard. So you come to me and I will give you the full-blown take-home exam that I would give my other students last semester, and you can see, you know, some other problems if you want to. Okay? So again, you're supposed to go look at the syllabus on your own. I believe we're going to have quizzes, midterm and final. That's it, right? In this class, go back and look at it. But I believe the breakdown, 40, 30, 30, or something like that. Yeah, I can't bring it up. But yeah, I believe the quizzes, all your quizzes are 40%. Your midterm is 30, and your take-home is 30. But please go through that orientation video and watch it, because there's kind of an asterisk next to everything. Anyone remember the big asterisk with the grades who watched the video about the midterm and final? What is it? Exactly. You have a midterm final. That's the only test you sit down and take in this class. All right, midterm and final. Those tests will be problems like what are out of the book. They'll be similar to your homework. So they're not the problems that you would be at home doing and take you 3 hours to do one. They're very mechanical. That midterm and final, you must score 50% or higher on each one of them. If you come into the midterm, you score 30, you fail the class. That's it. You come in the final, you score less than 50, you fail the class. Understand? So, all right. Any questions for me? Anything you want to talk about before we get into this? Okay. The take-home stuff I give you, I used to be really adamant about work alone. Do your own work, right? Again, I'm going to try something a little different this semester. If I give you a take-home quiz, you are allowed to work together on the quiz. You can come to me for help, but you may not go to the tutoring lab. So the people in this room are the only people that you're supposed to work on that with, all right? I think that's fair. If I walk by the tutoring lab, which I've done before, I've just randomly walked by a tutoring lab and I'll see two of my students from Cal 3 sitting there with the tutor, and the tutor's on the board and he's doing the problem, the take-home problem. That would be considered academic, you know, this scholastic dishonesty, and that would be considered cheating, and you would just be dropped from the class or be given an F, all right? As long as we agree. I don't mind you working together and talking to me, but just don't talk to anyone else, all right? All right. All right, so the notes, all right? I'm going to go through these notes, and what I've done, all the notes for the entire semester are ready in Canvas, all right? And I've provided you the first 2 sections of notes. So this is 10.1, this is 10.2. I'm going to pass these out, but from here on out, I won't provide them again. So for 10.3, you need to bring that to class yourself, either print them off at home, or I encourage you, if you have a laptop, why don't you get the dust off of it and bring it to class, download the notes, and just sit there in class and look at your laptop and follow me. All right, you can do that. I don't mind, because it's a lot of paper. I mean, if you printed out all the notes for the entire semester, it'd probably be this much, right? So I'm not encouraging you to go use all that paper. Everything I do in this class follows these notes. That's it. Yep. So it's pretty structured. Here's 10.2. So if you could just take one, pass them around. I have more copies than students, so I didn't know how many I would have. How about the lighting in here? Are we okay with the lighting? You want a little more light? A little bit more light? We just need to make sure we can see some of the smaller stuff. So I'm allowing you to work together. There's a philosophical reason for that, and that's, you know, there's usually two major differences with professors in the way they approach things. I believe that most of you are going to go out into the real world and be problem solvers, right? I mean, most of you are choosing an academic path where you're going to be solving problems. Very rarely are you ever stuck in a room and they say, okay, you got an hour and a half to figure out this problem. You don't have anything to look at. Go. You know, it's very, very rare that that's the case. So what do you need to be good at? Communicating with others, your peers. You need to be able to be good at explaining something to someone else, be able to take an explanation, be able to put ideas together, collaborate on things, and come to a conclusion, right? I hope with this working together, it doesn't become just one really bright student sits there and just shares his or her work with everyone else. That's not the point. So trying to learn from each other is what hopefully you get from that. And then making some, you know, friends and, you know, studying outside of class, hopefully that'll happen. We'll see. Can't force you to do that. Some people like to work alone. So coming to my office for help. Normally, I like to see students at my office. We have outside my office, there's a big table, and there's a bunch of tables in the room, and students can sit there. You're free to come in and do your homework. You don't even have to visit with me if you don't want to. You can just come there. It's a nice, quiet place to do your homework. And if you need help, you can just, you know, go knock on my door. Or if it's something you really need some help on, I'll come out there and sit with you, and we can go through things. You can work on the take-home stuff there with classmates. And I usually have about, you know, 4 or 5 students that will make it a regular thing. They're there every day, you know, well, every class period or something. They're always there studying. And then what happens is we get towards the end of the semester, all the people whose grades are like right on the borderline, they start showing up like the last 3 weeks. And it's like, it's a little late now. You know, you need to have been doing this earlier. So don't wait. Don't get buried in this class because it's going to come fast. We're going to finish the book. All right, so we're going to do 4 chapters. And you know, you just got to get used to the pace. It's going to be pretty quick, all right? I'm going to stop talking. I've already eaten up 20 minutes of the class. All right, so like I said, Chapter 10 is our first chapter. We're using this book. So if you've been here, this is the same book we've been using. I'm sure you can find it online. I'm sure you can find illegal pirated copies of it online. You tell me. Chapter 10. Vectors in the geometry of space is what we're going to be doing. And 10.1 is the 3D coordinate system. So a little bit of notation here and just language. When we say we have a point in R1, right? R1 means what? What is R1? Like one-dimensional space, like a number line, right? Number line. So when we say x is equal to something, like x is equal to 0.95, then on a number line we move to the right 0.95 and represent it with a dot, right? So x equals 0.95 in R1 is a point. Big deal. Okay, now in R2, two-dimensional space, you have 2 axes, right? And to represent a point in two-dimensional space, you need to designate both its x-coordinate and y-coordinate, right? So we call this xy. Can you all see that all right? Okay. We call that xy an ordered, what? Ordered pair, right? It's a pair of numbers, but the order matters, right? If you can't switch the x and y because that might possibly switch where that point is. So the order of this matters, the x, then the y. Then it represents a point in two-dimensional space. If the x-coordinate is positive and the y-coordinate is negative, x is positive, y is negative, then we are in the, what are these things called again? Quadrants. We are in the 4th quadrant there. Why is it numbered? It's 1, 2, 3, 4, right? It goes around like this, 1, 2, 3, 4. Why is it numbered counterclockwise like that? Yeah, because your angle always starts out down the x-axis, and then as the angle increases through positive numbers, it's right positive angles, right? 45 degrees, then 90 degrees, and then you keep going. So it's natural to want to move from the first to the second to the third to the fourth. That's why we number it that way. Just a little subtlety in case that somehow got by everyone. So what if I sit there and I say you're in two-dimensional space, all right? You're in two-dimensional space. And I say x equals 2. What's x equals 2 in two-dimensional space? All the ordered pairs that has an x value, the x coordinate is 2, right? What about the y value? It can be anything. It can be anything. So we say it's free, right? We call it a free variable, basically. So if you have an equation where your x is a number and your y is free, then you don't get a point. You get all points with that fixed x value, and your y is free, so it actually creates a line, right? A vertical line in this case. So that's a big difference. What I'm trying to get you to see is that if I say, hey, what's x equals 2? What does that look like geometrically? The first question you should ask me is, what space am I in, right? Am I in R1 or R2 or R3, R4, right? Like x equals 2 means different things in different spaces. In R1, it's a point. In R2, it's a vertical line. What is it in R3? We'll see. Make sense? Okay. Now, if we switch it around and we say y is fixed and your x is free, so we can pick our y to be anything we want. Our x value is free, so all our x coordinates can change. Then we get our horizontal line instead. Now, we also know that in two-dimensional space, R2, we can have relationships between the x and y coordinate, right? The ordered pair, we can define the y coordinate as a function of the x. And in this case, if y and x are the same, we get this thing called the identity, right? You all have seen that in the past. Y equals 3x is a line with slope 3, right? Y-intercept 1. Y-intercept 0. Negative slope, line slopes the other way. All right, so now what we need to do is talk about R3. So if you're in R3, you don't have an ordered pair. You actually have what we call an ordered, what do you think? Triple. We call it an ordered triple. Right? So in R3, you have an ordered triple. You have, instead of 2 axes, you have 3 axes. You have the x-axis, you have the y-axis, and you have the z-axis. Now, before I show you all this on the projector, I want to just talk about it in this classroom so that throughout the semester, I'll often reference certain things in the room. So let's just all agree on something. Imagine that the corner of the room down there, okay, where all the walls come together down the bottom, that's what we're going to consider the origin. That's going to be the point 0, 0, 0, right? And then if you follow the edge that goes along this wall right here, where the floor and this wall come together, that's going to be our x-axis, all right? Our y-axis, well, you know what? Our y is going to have to go that way. So let's do it different. The x-axis will go that way, okay? The y will come this way. And then your z is going to go this way. Now, we'll talk in a second about the right-hand rule. In 3D, you have to draw your axis a certain way. So x is along that way, y is along this way, z is up that side. Everyone okay with that? So if you give someone an x, a y, and a z value, it tells them how far to go out on x, then how far to come out this way on y, and then how far up and down to go on z. Yes? Now, here's that same sort of picture. Here's two-dimensional space. Now, it's kind of tilted a little bit, but that's 2D, right? X-axis, y-axis. But if we imagine now a third dimension that comes out towards us, right, the z-axis, then that's our 3 space. So I'm just going to tilt it now, and now you can see the 3 axes. I've got to get that plane out of there. Let me rotate things around. Make sure I get this right. All right, so let's take an x value. So you see that? I came out an x, so that's like I came out that wall, right? That point right there is the ordered triple 4.800. It just went out 4 on the x-axis. The y and the z were both 0. Now, if I change the y value, it'll come out the y like this. And notice that as it comes out, y value, that distance is the same as this distance, right? If I tilt this up and look at that point, it should be like a plane, shouldn't it? Plane, a flat sheet, like that, right? That still lies in that plane, doesn't it, that point, because I haven't gone up or down. So now what I'm going to do is go up. No, I'm not going to do that. I'm going to go up by doing that. And so now you can see your x, y, z. Everyone got it? Yeah? Nothing fancy here? All right, now, what would happen if I come in here and I say x equals 2 now? What does x equal 2 here mean? So all ordered triples, right? Where your x value is 2, your y value is free to be whatever it wants, and your z value is free. So let me try and fix this. I don't even know if I actually have 2. Yeah, I can go 2 here. So there we go. That's x equals 2 right there. So my x value, I came out on the x-axis 2. Then I moved some y and some z here. But let me show you the whole thing. X equals 2, all the points. There it is. A speckled plane. I don't know what's going on with the projectors drawing these little spots everywhere. Can you all see that plane? All right. So if it were here, what would it be? If we were back in the classroom, I would have gone out 2 that way, right? And it would be a plane which way? Like this, right? See, because if I take this point right here, the x value is 2. Take another one here, the x value is still 2, and then I can go up and down and left and right. So anything on this plane would constitute x is 2. So x2 is a plane in 3-dimensional space. So x equals 2 in R1 is a point. In R2 it's a vertical line, right? And in R3 it's a plane. Now there's some important planes in 3D that we'll use throughout the semester. One particular one is x equals 0. That means I don't move out x at all. I stay at 0, but I let y and z be free, which would be what? In this classroom, what would it be? Anything on this wall, right? That's x equals 0. We call this x equals 0, we call it the yz plane. The yz plane, because this plane includes what 2 axes in it? The y-axis is in that plane, right? And the z-axis is in that plane. So we call it the yz plane. Understand? Now what if we did y is 0? What would that look like in 3-dimensional space? What would y equals 0 be? It'd be a plane again, right? Y is 0. So that I'll put x is 0 back up here so you can see both of them together, right? So x was 0 was this plane, which we called the what? YZ plane. Y is 0 is that one. So what do you think we're going to call that plane? The XZ plane, right? XZ plane. And then the last thing would be Z is 0. What Z is 0? That's right. We call it the XY plane. It's the floor, isn't it? Okay. So throughout this semester, when we see an equation like Z is 0, we're talking about the ground, aren't we? The floor in 3-dimensional space. When we say y is 0, we're talking about the xz plane. And we have to just become very familiar with that, very comfortable with that. All right? Notice that those three planes that I drew there are all perpendicular to each other, right? Like the, let me take this out. Those two planes are perpendicular. If I look from the top, you can't even see them, can you? They're like this. And I could do that for any of the planes. Are those two perpendicular? Yeah, they hit it across, don't they? 90-degree angle. We'll talk more about that later. We say they're orthogonal and all this other stuff, but we're not quite there yet. All right, so that's the basic idea of what a point looks like in R3, what the general planes look like. I want to add one more thing. When we said x was 2, right? Here was our picture, right? That was x is 2. Get that out of there. I've kind of spun things around, but there's x is 2, right? I said that there were three important planes that we use a lot in this class. The xy plane, the xz plane, the yz plane, right? Those are the ones where it's x is 0, y is 0, z is 0. This plane, x is 2, is parallel to which of those other planes? Which is x equals 2 parallel to? The yz plane? Everyone understand that? Okay, so whenever I give you planes, you need to make sure you understand, which of those three important ones it would be parallel to. Now, are all planes in three-dimensional space parallel to one of those special three? I mean, I can tilt it right and then it's not anymore, right? We're looking at very special cases right now. Kind of like before in R2, we looked at vertical and horizontal lines, right? Here we're looking at the major coordinate planes. That's what we're doing. We'll get to general equations of planes later on. All right, now, the right-hand rule. Y'all have heard of this before? Physics people, I'm sure, have. It turns out that when you draw three-dimensional space, there's a way to draw it so that the structure of the space is different if you draw it using axes in a different way. So there's different ways to draw the axes, different ways to draw the x, y, z. And if you do it different than I do it, then the math that I do won't match up with the math that you do. We all have to agree on how we want to label these things. So we use what's called the right-hand rule. Right-hand rule says that if you take your right hand, and your thumb should always point out the z-axis, your fingers should curl from the positive x to the positive y. So back in this room, right? I take my thumb. If I'm going to say that's the z positive axis right there, then these fingers right here should go from the x-axis and curl to the positive y-axis. Got it? Remember when I first started, I said, let's call this the x-axis, right? If I had done that, where would my y-axis, positive axis, have been? In the other room, right? So that's why I changed it to that being x and this being y. So we all have to agree on that. Now let's talk about that a little more, because you're taking that on, not on faith, but let's just investigate that a little bit. Let's look at two-dimensional space. Now when I write x, y, I want everyone to understand what I mean is this is the positive direction of x, this is the positive direction of y. That's the normal way of writing the R2, isn't it? Would it be incorrect if I wanted to say, call this the positive direction and this the positive direction of y? Could I do all the math, all the Cal 2, all the Cal 1, everything that we've done, could we do it by someone else coming in and defining their two-dimensional space to look like that? Would it all be okay still? Yes, it would actually. And the way that the easiest way I can explain it, where are the notes? Any extras? Here we go. Here's, well, you know what? I can use this board. I just happen to have a rolling board in this class today. I think the paper will work better. Don't worry about that. Here's our traditional XY, right? And I'm saying, is it okay to go from that to that? Well, all I have to do is take this sheet of paper and turn it over like that, And wouldn't I have that? Can y'all see it coming through the marker? It was X and the Y was up here like that. Y'all see that? So all that one is just standing on the other side of the room, like the other board, like the other room, and looking at this transparent and seeing through it. It would be the same thing, wouldn't it? Understand? If I changed it and I said, all right, could I do that? Well, what is that? Just flip or just rotate it? All you're doing is taking this one, right? I'm all confused. And just rotating it like that? Okay, this idea of rotating and flipping and stuff without actually changing the space, leaving it fully intact, is called an isomorphism. That's a more advanced math thing. I'm not trying to throw fancy words out there, but I'm saying that there is a way in math that what we do is we try and say, if you make a change to the space, is it still the same? If it is, it's isomorphic. And so these two spaces are isomorphic, but whoa, in 3 space, you can't do it. Those two are labeled different, right? This one follows the right-hand rule, the first one. The other one does not follow the right-hand rule. There is no way that I can move things around or rotate or do anything to make that the same as this. Does that kind of make sense to you? And since you can't, they're completely different spaces. And so you can't, they don't agree. If you start doing math here, it's not going to agree with the math that would necessarily be done there. So that's why we have the right-hand rule, is so that we all agree on the same thing. It's kind of like order of operations, right? We have order of operations, parentheses, exponents, all that stuff. Well, we do that because if we didn't, then our math wouldn't agree, wouldn't it? You would get one answer, I get a different one. All right, so that's our little right-hand rule thing. Yes.
Another question, arguing that they're not the same space, because I
Mm-hmm.
they're not, but as long as they're so labeled, not that we would want to do it, theoretically are both of them legitimate spaces, although you can never use for one.
Absolutely. Absolutely.
You have to redefine everything for yourself.
That's right. That's right. I don't know if any of you ever did this in Cal 2. You may or may not have seen this. Like, there were times when you were trying to integrate, and maybe you had two functions that went like this, and you're trying to maybe find the area in here. And both of those are not functions of x, right? Here's x, here's y. They're not functions of x, but they're both functions of y. So you could, I'm just going to make up something here, and it, may not even be correct, but let's say one was y squared and the other one was 2 minus y squared. I know those don't look right, but if that's what you had, right, then you could integrate that. You would integrate it with respect to y instead of with respect to x, right? But it turns out that what you could do in this problem, again, I don't know if you ever saw this, is just change all your variables. Make this x, make this y, make this y equals x squared, make this one y equals 2 minus x squared. And basically what you've done is, now you're looking at the problem, just turn your head like this. Oh, actually, we need to be on the other side of the board, okay? Be in the other classroom with your head turned this way, and now you have the x-axis and y-axis like this, and they are both functions of x, aren't they? And now you can integrate with respect to x, and you can have your calculator graph those a lot easier, right? Because they're now in terms of x instead of y. So any time in Cal 2 that you had these weird things sideways, you could have just switched x and y completely, and you have the exact same thing. In R3, you can't do that. So yes, it's a legitimate space, but you can't work with it like you could have done here. I hope that addressed your question. Okay. All right, now, we were talking about in two-dimensional space that you had the four quadrants, right? So in three-dimensional space, does it seem natural that we would have 8 sections? We call them octants. And so to be in the first octant would be to be in this classroom, all right? Because if I pick any point in this classroom, like the projector, there's a positive x, right? There's a positive y, and there's a positive z. So that ordered pair up there, all the coordinates are positive, aren't they? That's the first octant. So anything that lies in here is the first octant, isn't it? That keeps on going out forever. Then the second octant is going to have a positive x, and then my y, instead of being positive, well, hold on. No. I have my conditions here. Negative x, positive y. Sorry. Second octant, we still follow that counterclockwise rotation. So what we're doing, first octant's in here, positive x, positive y, positive z. Second octant, we have a negative x. So we're in the other classroom, right over here. Negative x, positive y, positive z. So it's the projector in the other room. Do you all see that? That's your second octant, so anything in there. And then our third octant would be where? So we've gone from this classroom to the next one, and then where would that next one? Over there, right? So not outside, but over there. And then above the floor. So that's everything in that back corner like that? Yes? Yep. I'll put these here. Ooh, they're not coming out very good there. You're supposed to be able to see those down there. Okay, so octant 3, x is negative, y is negative, z is positive. So here's the summary. I don't think that's on your notes, right? Yeah. So this is us in our classroom, right? The blue one is that classroom. The red one is back there. And then now the fourth octant would be everything in that green one right there, which is right out the window, isn't it? Okay. Now, where do you think the fifth octant is? Beneath the first. So here's our first octant. Our fifth one's below it. And then the sixth one, we're going to go kind of like that counterclockwise again. So here comes octant 5 down there. Octant 6 is over there. 7, we're not going to be able to see 7, right? And then here comes 8. See 8 in the back corner? Yes, that's exactly right. Here's the summary of all of those. I'll try and make it show up here. Yeah. Because of the projector, it's hard to get this to show up. The book talks about this too. Okay. Next note. So some surfaces in three-dimensional space. I think we talked about some surfaces already, didn't we? Planes. X equals 0, y equals 0. Then we can move them left and right, up and down. So these, we're just going to call these like the coordinate planes, all right? These are our coordinate planes. Those are some examples of surfaces in 3D, but they're definitely not all of the surfaces in 3D. Okay, now we get to our first formula, all right? Formula is, so this is day 1. Sir? Okay? Don't fall asleep. What happens if you fall asleep in this class? 10 points off your exam, and you get kicked out and you're counted absent. Okay? I just don't want to make an example that first day. It's too early for that. Pardon? Okay, you didn't look awake, but all right. Do what you can. Go out and do some jumping jacks or push-ups in the hallway or something. Get your blood flowing if you have to. So we have a formula. Sorry, I lost my note there. Come on. All right, so if you have 2 points in three-dimensional space, x, y, z, and RST, the distance between them is given by this formula. Does that look familiar? It should look like the distance formula from two-dimensional space, with one exception. You actually have this third part, right? This third piece. So how would we find, how could we come up with this formula? Let's just think about it. We're not going to actually go through it. But let's say I was trying to find, see if you can follow this. If I was trying to find the distance between, let's say, the origin and that projector, even though this formula is more general, it goes from any 2 points. But let's say I'm just trying to find the distance between the projector and the origin. Now, I know the coordinates of that point, okay? I already know them. Let's just act like we know them. Then how could we find it? Well, okay, so the distance we want is the line segment that goes from that projector down to the origin, right? So did everyone see the line connecting those? We want to know that. If we take a line and we drop a line straight down to the floor and then back to the origin, I've just drawn a right triangle in three-dimensional space, right? If I know this side, the bottom, and I know that side, then I have two sides of a right triangle I can solve for the third, right? Do you know that shorter side right there? The one from the ground to the projector. Do you know that? That would be your z coordinate, wouldn't it? Remember that has an x, a y, and a z, doesn't it? The z is the up-down. So you already know that side, don't you? The only thing is you need to know this. Do you know that? No. But now, do you see that the point on the ground to the point to the origin? Do you see that that is the hypotenuse of another right triangle? It's the one that goes the x this way and the y that way on the ground. Do y'all see that? The y there, the x over there, here's your hypotenuse. So you know that x, you know that y, so how do you find this one? This one would be, if that's x and that's y, what would this one be? Square root of x squared plus y squared, right? Now that's this side, right? Square root of x squared plus y squared. Take that and then that one. So take this and then square it, right? So now you have what? X squared plus y squared. And then what's this one? Z, so square it. And then that side is the square root of all those added up, right? So it would be the square root of x squared plus y squared plus z squared. That's what you would get if you were from the origin. But now if you translate everything, then you would get this formula. So it's a little exercise you could do for yourself to convince yourself that that's true. But it is really just two applications of right triangle geometry. That's all it is. So there's our formula. I won't talk any more about it. You just need to know how to use it. And now the first real big equation of a geometric shape in three-dimensional space, and that's a sphere, is one of our most basic shapes. A sphere in R3 has the equation x minus h squared plus y minus k squared plus z minus l squared equals r squared, where HKL is the center of the sphere and r is the radius. This looks familiar also, doesn't it? You should remember from equations of circles, right, in 2D. If you have, it doesn't matter where the origin is, if this is your center, HK, and your radius here is r, then it was x minus h squared plus y minus k squared equals r squared. That's the general equation of a circle in two-dimensional space, centered at HK, radius r. So all we've done is added, again, this third piece, this third element to the equation. We've added the z minus l squared. So you can change, if you change your center, your h, or your x, your y, your z, bless you, and then your radius, you get this sphere, right? Any questions? So this is a coconut, I'm calling it the coconut problem. Let's say it's not really a coconut, but it's a sphere, okay? And I've cut it in half. Well, you know what? Let's not cut it in half. Let's take an entire sphere and let's hollow out part of the inside. All right? So take out some of the inside of it. Solid sphere, take out the inside. So if it's a solid sphere, maybe we shouldn't call it a sphere. We should call it like a ball. So we could distinguish, right? Sphere means just the outside. Can we agree on that? The ball would mean the outside and everything in it. So we've got this ball. It looks like it has a radius of, man, it's hard to tell here, 8. I'm looking from the top here. It looks like a radius of 8. And then the one on the inside looks like it has a radius of what? 5. Can we just agree on that? We've got a ball, and then we've hollowed out, we've taken out another ball on the inside that has a radius of 5. So I'd like for you to explain to me, I'd like for us to try and explain to somebody else, without the picture, what every point that lies in this coconut looks like, or what are the conditions for all the points that lie in that coconut. So one of them had radius 8, right? And then the other one had radius 5. Would you agree that would this point live in our coconut, somewhere in our coconut? Would that be on our coconut? Well, no, a coconut has like a shell and then the inside's gone. So you have some thickness to this ball still. Would that point lie in the coconut or on the coconut? Yes? Okay, would this point lie in the coconut? Yeah. This one? Yeah. Okay. This one? No, that wouldn't work, right? So how do you explain to somebody all the points that live on the coconut? Every one of them. What's the easiest way to explain what that is? I think what you're trying to say is that the distance from the origin is always greater than 5, right? 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 Because you could possibly have a scenario where one of the coordinates is not bigger than 5. Right? I mean, look at all those points. Some of the coordinates are 0, so the distance has to be greater than 5, but it has greater than or equal to 5, but it also has to be what? Not past 8, right? So here's the best way to do it, all right? The cleanest, easiest way. We want our sphere, our ball, our coconut, to be basically a sphere with a variable radius. Would you agree? So if I wrote this down right here, what was it? If I wrote that, that's the equation of a sphere, right? Where is it centered? 0, 0, 0. What's its radius? 8, right? That's a sphere centered at the origin, radius 8. Everyone see that from the formula we just had? Okay, that's the shell. That's the outside of the coconut, right? Now what I need to do is make sure that I get everything inside, but I don't want to go past a radius of 5. So what I'll do is I will scrap this equality, and I will switch it out with an inequality. That would give me what now? What's the difference between that and the equation? Yeah, it's the sphere, the edge of the sphere, and everything inside of it, right? All the way down to the origin. I don't quite want that, do I? I want to make sure, though, that this piece stops at a radius of 5. So what I need to do is on the other side of this, throw in 25. Does that make sense? You need your x, y's, and z's. The condition on those coordinates of the point must be that because this looks like a sphere, the radius, right, is less than 8, and the radius is greater than or equal to 5. Less than or equal to 8, greater than or equal to 5. So hopefully you see that. It's like, I'll call this R1 squared less than equal to x squared plus y squared plus z squared less than or equal to 8. R2 squared. So what we're doing is we're bounding the conditions of our points between these two radii. Make sense? All right, let's try something a little bit different, a little bit more challenging than that. Yeah, bless you, bless you. All right, so what I'm going to do is I'm going to put up a couple of problems here, one at a time. I'm going to give you a couple of minutes or a couple of seconds, I don't know, it depends on the problem, to kind of think through it yourself, maybe talk with your neighbor. We'll start getting to know each other a little bit here, and then I will ask for like ideas on how to approach this. All right, and then I'll go through the problem myself. All right, so the first one, by the way, these examples are not in your notes. I just kind of threw these together real quick. Find the equation of the sphere centered at 1, -2, 4, which touches, what I mean by that is tangent to the YZ plane. Okay, so it's 11:59. I'm going to give you a minute or two to not necessarily come up with the answer. It's not necessarily what I'm really after here. What I'm after is, do you have the attack, the plan to go after the answer? Do you know what you're going to do here? Okay, so think through it. Talk to each other if you'd like. I know it's day one. Everyone's so damn shy. You know, whoa. You got it over there, you think? Let me see. Okay. No, it's okay. I can understand that. Ooh, Fujitsu. What is that? Is that the? It is. That's what I have. I have Fujitsu. Yeah. It's nice. Still working. Yeah, it's still working. Okay. I don't know if that's right. I haven't even really thought about the problem. I mean, I'm just seeing what you, if you all agree with it. You all agree? Yeah, we're gonna talk about it. But you all agree with it. Three of you? Okay. All right. Okay. I'm gonna give you one more minute. Okay, I think that's sufficient. Any volunteers on, I don't want, like, don't give me the equation, but what's the approach here? Anyone want to tell me what their approach is to this? Okay, good. Basically what you're saying is you already know most of the equation, right? You know H, K, and L. That's given, right? For what we know about equations of spheres, you need to know what the center is, H, K, L, and you need to know the radius. If you have those, you've got the whole thing, right? I already give you the center, so you know H, K, L. You just need R. Okay, so what's your thought on how to get R? Mm-hmm. Okay. So how far is the center from that plane, and how far is it? So how are you determining that it's 1 unit from that plane? Okay. Okay, good. So let's just talk about it this way, okay? That's all correct, but let's try and just look at it visually. If you all get it, good, but I'm just going to kind of baby step through this today. Let's say that my little desk up here thing was the center of the sphere, right? I want to know how far away it is from the YZ plane. So where's the YZ plane? Right behind me, right? This is it. So it doesn't really matter how far over it is. It doesn't matter how far up and down it is. Just this distance is the only thing that matters, right? And this distance is the x-coordinate of that point. And the x-coordinate of this point is 1. So it's 1 unit away. Now, let me try, if I can, because I think it's a good exercise for you. What if I was trying to draw this point in three-dimensional space? There's like 4 or 5 different approaches to how to draw three-dimensional space on a two-dimensional piece of paper. So I'm going to show you a couple of variations. Always following the right-hand rule. Here's one way to do it. You draw an x-axis that comes out kind of towards you at an angle. Your y-axis goes out horizontal. So this is kind of like, this right here and this right here is kind of like the x and y used to be, but now you have this one coming out. This, we could call this x, we call this y, we call this z. Would that follow the right-hand rule? Yes. Now again, x, y, z, because I've labeled x, y, z, those are the positive directions. Now keep in mind that the y-axis does extend this way, doesn't it? But that's the negative y direction. The negative x direction is this way. And then the negative z goes down like this, right? Everyone see that? That's one way to do it. Here's another way. You draw kind of a flattened out x. Actually, that's not even flat enough. I'm going to redo it. Flatter than that. Like this. So don't draw this. I'm not saying draw that. I'm not saying to draw this. I'm saying take this x and like flatten it out and then make your z-axis come up. Now if you do it that way, this has to be your x, this has to be your y, and that has to be your z. So that you follow the right-hand rule, right? It's just a different way of viewing this same thing. It's just, depending on what class you're in, instructors or books, they'll draw the axes different ways. But it should all be the same, right? As long as we follow the right-hand rule. Let me work off the one off the left. You will see me in this class switch back and forth from one to the other when I'm drawing up here. Because I think it's a good, we don't want to get fixed on one way. We want to be open to different approaches. So let me work with this one. Where's the point? 1, -2, 4. So how do I draw that? Let's say that I come out on the x-axis 1. Let's say that that's 1 right there, okay? So I'm going to come out this way. This is a little tick mark. Remember how we used to do tick marks on axes? Notice that my tick mark runs parallel to the z-axis. Okay. Now I need to move which way? The y-axis -2. So where's -2 on the y-axis? Well, here's a tick mark. That's -2 on the y-axis. So I need to come out the x, 1, and then go to the left, -2, right? So how do I figure out where that point is? Watch the way I draw this. From -2, I'm going to draw a line coming out like this. Notice that line is parallel to what? The x-axis, right? And then I'm going to come and meet it with another line this way, which is going to run parallel to which axis? The y-axis. Like this. Now, if I wanted to, I could extend another one like this. You know, extend another one. And what I'm doing is I'm trying to show you I'm drawing like a grid. And that grid is like a piece of graph paper on the ground, isn't it? So now I'm here at this point. And now what do I need to do? I need to go up 4. So 4 on the Z. So watch my tick marks. What are my tick marks running parallel to? The x-axis, right? There's 4, right? So how do I get to that point? Well, I could go up like this and then over. Okay, so I came up from the 2 here, right? Here's 2. Came up to meet it, and now I need to come out, what, how many? 1? I mean, there's so many different ways to do this. It's just, you've got to make all these coordinates meet up in one place. So I'm trying to figure out how far up, right? How far up is 4? So what I did was I went up 4 here. I came over 2, and then I'm going to come out 1. And that should be it, right? That should be the point. So getting decent at drawing three-dimensionally is a skill that you just have to try and pick up. They actually have 3D graph paper. Has anyone ever seen 3D graph paper? It's a bunch of lines. I don't have it with me on this computer. I don't think this has 3D graph paper. No, it doesn't. It's graph paper that looks like this. And then I think the other ones go like this. Something like that. And then you go down like your X and your Y. You meet up, and then you go up Z. It draws everything already kind of tilted for you, so you can kind of follow things. But you don't have to have it. Just be aware it's out there. Yeah. All right, so now, this was the center of my sphere, and I wanted to know how far away it was from what? The YZ axis, which is this back wall, isn't it? So maybe from this you can see that the distance there was the x-coordinate, was 1. Okay, we good? Next one. Find equation. Oh, we didn't find the equation. Oops. What's the equation? X minus 1 squared plus y what? Plus 2 squared. I'm just doing HKL, right? Z minus 4 squared equals 1. Next. Find equation, sphere, centered, same center. 1, negative 2, 4. Touches z-axis. Z-axis. Not XY plane, not YZ plane, Z-axis. Just touches tangent to the Z-axis. I'm going to pass around the sign-in sheet. Make sure you find your name, initial next to your name. That's the way I take attendance. I'll do that every day if I remember. Anyone have it? Anyone think they have it? Yeah? So where are you getting the radius from? Mm-hmm. Mm-hmm. Okay. Do y'all see the difference in this problem? I mean, there's a difference, right? From this and the one before? Not as obvious as the one before would have been. Another minute. Okay, I'm going to go ahead and go through this. Here's the point, right? It was 1, -2, and then 4. We've already graphed that, right? And we want it to just touch the z-axis, run tangent to it. So what we want is our radius of our sphere to go out and touch the z-axis right here somewhere, right? That's our radius. And so what we need to see is that that's not our x-coordinate, that's not our y-coordinate, right? It's actually a combination of the two. So I'm going to have to kind of really push it to get you to see this, I think. Thank you. Do you all see that right triangle? It's laying flat. It's parallel to the what? That triangle would be parallel to the what plane? X, Y plane, right? That up there. And so if you take it and you look at it from the top, it's this. We're trying to find that red line. Do you all see that? Now, what's this side right here? That side's 1. This side over here is 2, right? The magnitude, the length of that line is 2. So the hypotenuse, right, is square root of each one of those squared. 1 squared plus 2 squared is √5, right? That's your radius, square root of 5. So the equation becomes x minus 1 plus y plus 2 squared plus z minus 4 squared equals radius squared, so 5. Make sense? What would be the difference if I changed the problem I said where it just touches the x-axis? It would be this triangle right here, wouldn't it? Be that one instead? We're going from the center down to the x-axis, okay? So the radius would be this squared plus this squared square root. So what is that, 2 squared? 4 squared, 16, right? 20, square root of 20. So that equation would just change to 20. Yes? Okay. All right, now that is that's pretty much it for this section. Well, I won't do this problem, but I'll ask you how you would do it. If I put this equation up here, x squared plus y squared plus z squared plus 8x minus 6y plus 2z plus 17 equals 0. And I asked you to show that that's the equation of a sphere. Show that that's the equation of the sphere, and tell me what the center and radius of the sphere are. Well, it doesn't have the format that our sphere equation has, does it? So in order to figure out what center and radius would be, you would have to make it look like this. You have to turn it into this. Do you agree? If you could somehow get your equation to look like that instead of that, then you would have the center, right? And you would have the radius. So how do you think you could get that to happen? That's right. You could look at these x coordinates, or the x terms, the terms with x's in them. You could group those together in the front like this, and you could complete the square on those two. You can complete the square here, right? And then do the same thing for the y. And then the same thing for the z. And then what about that 17 at the end? Well, I could take it to the other side, couldn't I? If I wanted to. So I can complete the square on these two, complete the square on those two, complete the square on those two. If I do that, then I should be able to get something that looks like this, shouldn't I? So if you don't remember completing the square, then you'll have to go back and look it up. I will ask you, though, this is just more for my own information, separate idea here. Same idea, but separate sort of problem. If I gave you that right there, and I said complete the square, how would you do it? That's it. That's the whole thing right there. I said complete the square. What would you do? Well, that would be factoring it, but I'm saying turn it into something like, x something squared, like that expression. Turn it into that. Okay, good. So let's go. Maybe we go back to this. How do you complete the square on that? No, has it been too long since you completed square? Divide that by 2, which is 4, and then square it. You get 16. What do you do with that 16? Add 16 minus 16. How many of you add 16 on both sides? Right? Okay. This is why I'm bringing this up. There is a preferred way. I like to make sure everyone kind of follows along here. If you have learned to take half of that, square it, get 16, and you've learned add 16 on both sides, that's not incorrect, but I do not recommend it because there's nothing that says that you're always going to be working with an equation. Right? You can't add 16 on both sides if you don't have an equation. Like this is not an equation. So you can't take half of anything and then add it to both sides. So instead, you add and subtract it. So you add 16 and subtract 16 at the same time. But I'm going to do it on this one instead. So before you can complete the square, you have to get rid of the 2. I can't divide by 2, though, because there's not an equation. But I can factor 2 out. If I factor 2 out of 5, I get 5 halves, right? So if I distribute that back through, I get back what's up there. So I haven't changed the problem. Now, this is my b. I take half of that. What's half of that? 5/4. Square it. 25/16. So what I do now is I say that that's the same as 2x squared minus 5 halves x. I'm going to add 25/16 and subtract 25/16 at the same time inside that parentheses. So I still haven't changed the problem, right? This is the same. This is just 0, right? So I haven't changed it. But those first 3 terms in here are guaranteed to factor. I'm going to change the brackets here to be what? X. And remember what it will be? It was whatever this was when you divided it by 2. But you have to keep track of signs. So it's negative 5/4. That's the thing that we had squared, right? The 5/4. So that's what goes in here. Negative 5/4 squared. So if I take this right here and I square it, I should get these 3, right? Then I have the minus 25/16. And then finally, bracket, distribute the 2 back through. So I'm just going to throw the 2 in front of that parentheses because I can't push it all the way through, can I? Order of operations, right? I couldn't do that. Can't put the 2 in here and here, right? Please don't do that. That has to stay. But then that 2 goes to the other one, becomes what? Negative 25/8. This is the correct way to complete the square on an expression. And I recommend you just be able to do it this way, whether it's an expression or equation. Now, on your homework, you'll have to do things like this. Complete the square, complete the square, complete the square. You'll have a bunch of constants. You take them to the other side, and that'll give you your radius. What I'd like for you to look at for homework tonight is going to come off of page 541 in the book. It's going to be number 7, 8, 10, 11, 13, 15, 18, 19. That's good. Now we still have 15 minutes, so I'm not done, all right? Just so you know. There are going to be problems in the homework that I did not demonstrate, all right? I would get used to that idea, all right? Don't ever assume that, okay, well, he didn't do it in class, so I don't know how he's expecting me to do it at home. I mean, normally, you should be able to do these problems if you think through them enough, all right? Okay, let's start the next section in the last 15 minutes, 14 minutes. Oh, I don't collect homework. I don't collect it. But hopefully, as a Cal 3 student, I don't have to tell you that your homework is important to passing the class. I will answer questions on homework, yes. I won't take 30 minutes of class, but yes. Oh, yeah, absolutely. That's what I want you to do. I want you to come for help. I'm going to give you your first take-home quiz on Wednesday. So be careful with this because this is something that gets a lot of people in this class. I don't pick up the homework. You don't get a grade. I'm just not going to do it. When I give you those take-home problems that are pretty tough, I've assumed you've done this. Okay? The assumption is you've already done this stuff. So this stuff that kind of builds up the basic foundation of what you need for those harder problems. So if you're doing a problem, you're looking at that take-home quiz, you come to me for help, and you're looking at it, you have no idea, and I'm like, well, look, I mean, on this one, you just have to find the equation of the sphere, and it looks like this, and you're like, I have no idea, I didn't even know that that's the equation of a sphere. I'm like, well, you didn't do your homework. You haven't looked at the notes enough. You're not comfortable with this yet. You know what I'm saying? You have to get some level of comfort with the material before you can go and take these more challenging problems on. But you should have it done by the next class. That's the way I always look at homework. If I give you a homework assignment, this should be done by Wednesday. When you walk in, I should be able to ask you a question on that, and you should be like, yeah, okay, that's good. Or you ask for help in the beginning. Okay, I could not do number 13. All right, next section. 10.2, vectors. How many of you have heard of vectors, done some vector stuff? Yeah? All right. In this class, we are going to look at vectors as having 2 properties. We define a vector as an object that has the two properties of having a magnitude and some direction. Magnitude meaning length, and direction meaning an angle or something like that. So here's an example, the geometric idea behind a vector in two-dimensional space. It's like this arrow, right? This arrow has a length to it, and it has a direction. I can change the vector's direction. I can change its length, right? Now, in three-dimensional space, we have an arrow, same thing, right? The question becomes, though, like in this one right here, if I say what's the direction of this, we could all probably say it would be the same as that angle, right? Like the direction, we could say it's whatever that angle is, that's its direction. But when you're in 3D, how do you talk about direction here? You know? Like what angle are we talking about? Relative to what? So we'll address that. Just right now, let's keep that in the back of our minds as something we'll be looking into. But let's get some of the language out of the way. For a vector, we denote a vector with this little half arrow. That lets you know we're talking about a vector instead of a line segment. A line segment is just a line that it goes from one point to another. That's a segment. This is a vector, two different things. So whenever I want you to know that, I'll put that little half arrow on top. Now, the book, or a lot of books, instead of doing that, they will use a bold V instead. But it's hard for me to write with bold when I'm writing. And it's hard for you to write in bold when you're writing, so we use that instead. We all understand we're talking about a vector. You have what's called the initial point of the vector, and you have the terminal point. We call this the tail. We call that the tip. Okay? This is also known as, or referred to as, what's called the displacement vector. All right, two vectors are said to be equivalent or equal if they have the same magnitude and same direction. Notice that the position does not matter. So look at these two vectors. We have this black vector and this blue vector. Do they have the same length? They appear to have the same length. Do they point in the same direction? Are they parallel? Yes. So they are equivalent. Meaning, if I call this vector u and this vector v, u and v are the same thing. Even though they're oriented in different parts of two-dimensional space, they're equivalent vectors. What if I move this one over? Same thing, right? Doesn't matter. Down, doesn't matter. They're still same length, same direction. As soon as I make one of them shorter than the other, they're no longer necessarily equivalent. Why is it that we want to be able to define something that where it is in space doesn't change what it is? Where in physics is that useful? What is always the same with my hand in this book here? Okay, that's a little more than I'm going for, but yes. What forces are acting on this book right now? Gravity and my hand going up, right? So I have two forces. One force going down, one force going up, right? And they're equal because the book's not moving. So if I move over here, has anything changed? No. Same force down, same force up. So that force going down can be looked at as a vector. It does not matter where I am in this space, that vector is still unchanged, right? That's the usefulness of a vector. If we define vectors, if we had to say not only is it a length and direction, but specifically this point and this point, then when I move, then everything changes, right? And I move again, everything changes. So we want vectors to be able to be moved around without changing them. Same thing with, you're dragging something across the ground, right? Or you're rolling a cart or something like that. You have a force, coming in the direction of your arm, pulling, and as you move, that force is staying the same. Well, assuming, you know, you're just keeping the same amount of pressure or whatever. So that's the usefulness of vectors. Now, if you have 2 points, right, 2 points, x1, y1, and x2, y2, then we can define, right, someone gives you 2 points. Here, that's in two-dimensional space, right? Someone gives you 2 points, you can always define a vector going from one point to the other, right? Or you go the other way around. So if we have 2 points A and B, and we want to define the vector that goes from A to B, then it's x2 minus x1, comma, y2 minus y1. So you're taking, if I'm going from A to B, then I take the x-coordinate of the second point, subtract the x-coordinate of the first point, and that becomes this new number right here. Then this one right here would be the y2 minus y1. And notice that we use these instead of parentheses. These are angled brackets, that's what they're called. And anytime you have numbers sitting inside of angled brackets, you're talking about a vector. Anytime you have numbers inside of parentheses, you're talking about an ordered pair, ordered triple, a point in space. There's a difference, right? So if you want to go the other way, you want to go from B to A instead, you switch the order, which should just change the sign, shouldn't it, of the number? So here's an example here. I have 2 points, right? I can move these points around, doesn't matter where they are. I can show you a vector that goes from A to B. Here it is, A to B. So we write AB with the little half arrow on top of it. And all I'm doing is subtracting the coordinates. Now, what I'm going to do now is I'm going to show you the other vector that goes the other direction. And I'll take the other one off. And so the arrow goes from here to here. But you subtract the other way, so notice the signs here were different than the signs here. They were opposite. Move them around, changes the values. Oh, look at that one. Zero here because the y's cancel each other out. So here's the same thing in three-dimensional space. If you have ordered triple, x1, y1, z1, x2, y2, z2, the vector from A to B is this. Vector from B to A is this. I don't think we're going to do that example. I think that that's too trivial. Would you agree? Maybe not. Let's just do the first one, and we'll just do it like pointing to the board. If I want to go from A to B, what's the first? Which one am I going to subtract from which? So the A from B. So I start here. I go -2. I take away 6. I get -8. So I get -8, and then the next part will be what? 8, take away -5. I get 13, and then 10, take away 6. I get 4. Did I talk? Oh, no. My note comes later, what I was about to say, so I'll wait. And then the other way, you go this minus this, that minus that. All right, now there is something called the zero vector. A bolded 0, or the 0 with the little arrow on top of it. In two-dimensional space, the zero vector is the vector 0, 0. And in three-dimensional space, it's the vector 0, 0, 0. So there is no zero, like 0 is different than the zero vector, is what I'm trying to get at. Now some language. When you have a vector, z, we had numbers in here, right? Those numbers are called the components of the vector. We have, the first number is the x component, the second number is the y component. How is that different from an ordered pair? What did we say with ordered pair? The 2 here would be the x what? X coordinate. 2 here would be the x component. When you're talking vectors, you're talking components. When you're talking points, ordered pairs, ordered triples, you're talking coordinates. That's the difference in those two. That's what I'm trying to point out in this note. Some language, some subtle language. So we use components for vectors, not coordinates. In three-dimensional space, of course, you'll have an x component, a y component, and a z component. Yes. Yep. It's a displacement of that in that direction of that coordinate axis, if that makes sense. So whatever the z is the displacement z up and down.
Yeah, like if you were to stick a book on a three-dimensional space,
Mm-hmm.
you have the highest resolution on it. That'd be like a moment, basically.
If I'm pulling, let's say I've got a rope tied to the projector and I'm pulling on it, the amount of force I'm pulling with, right? I could talk about the length of the rope, right?
Yeah.
And that would be connected with the coordinates, x, y, z coordinates. Components would be, I've got this rope, I'm pulling on it. I want to represent the force of that pull. That force is going to be represented as a vector. The harder I pull, the longer the vector gets. Okay, so the component would not necessarily be a spatial thing as much as it would quantify some other, in this case, the force. Yes?
Maybe you could say walking from here to there is the same thing as walking from here to there, walk that way and then that way. Those are the two components.
I know what you're saying. What I want to separate though is the idea of when you're trying to connect a vector to specific points. If you say like going from here to the projector, I go from here to there, I could go here, there, there. Those are all coordinates. Vectors, the components just give you a displacement in these directions. It doesn't matter where I am in the room. So, yeah. The parallelogram rule is kind of leading into this, but we're out of time. So we'll pick up right here on the parallelogram law for next time. And we'll probably blow through 10.2 pretty quickly. Remember, I'm not going to supply you with 10.3 notes. So if you want to be able to follow along in class, then you need to print them or you need to just bring your laptop and follow along. I don't have a problem with that. Or you could even just follow me in class. That's not a big deal. Just when I get to an example, you just need to be ready to write, if you're going to write things down. All right, I'm going to stop this recording and